Given the piecewise defined function f of x equals x squared minus x minus 2 over the quantity x minus 2 if x is not equal to 2, and 1 if x equals 2. Check continuity of this function and redefine this so that f is continuous everywhere. The function f is said to be continuous everywhere on its domain, so we would need to check the domain of each of the parts. The first part is defined everywhere when the denominator is not 0, but this part is defined so that x is not equal to 2. Thus, for any x value that is not equal to, this part makes sense. It is a real number, and so the third part is continuous everywhere except at x equals 2. The second part, y equals 1, is a constant function, so it is defined. Thus, to check for continuity in a piecewise defined function, we oftentimes check the limit definition for continuity at the x value that connects the first part to the second part. In this case, on the number line, the x value that connects the parts is x equals 2. If the function f is continuous at x equals 2, then it needs to satisfy the condition the limit at x equals to 2 of f of x equals f of 2. Now, f of 2 is defined to be 1. The second part, when x equals 2, y equals 1. And so f of a is 1. For the limit, we only consider what happened to the function as x approaches 2. At x approaches 2, we would have to use the first part because the second part is only at one single point at x equals 2. Thus, the expression that we will need to use to find the limit at x equals to 2 is x squared minus x minus 2 over x minus 2. The limit at x equals to 2, we factor out the numerator to end up with x minus 2 times x plus 1. The denominator is still x minus 2. Double check to see if we factored it correctly. X times x is x squared. X times 1 is x. 2 times x is 2x. So x minus 2x is negative 1x. And minus 2 times 1 is minus 2. And so this limit is now 2 plus 1 or 3. The limit is 3 at x equals to 2, and the functional value is 1, and 4 is clearly not equal to 1. And so we say that the function f is not continuous at x equals 2, but it is continuous everywhere, and so f is continuous on the interval negative infinity to 2 and then 2 to infinity. It is continuous everywhere except at x equals 2. And so how do we define this so that this function is continuous everywhere? Now, for the function to be continuous at x equals 2, the limit needs to agree with the functional value. The functional value is defined to be 1 at x equals 2, and so if we can redefine it, we would need to, instead of defining y equals 1 at x equals 2, we would define this as y equals 3 as x equals 2. And so if we were to move the point 2, 1 to 2, 3, we would fill in the hole and we end up with a continuous function. The new function that we would need to define is a piecewise function, f of x, or it is better to use a new name, g of x, equals x squared minus x minus 2 over x minus 2 if x is not equal to 2. And if x is 2, then we define f of x equals 3. Usually, when we redefined the function, we only redefined a point. In this case, we move the point 2, 1 to y equal 3 when x equal 2.